All right, so my name is Michael Tremmel. I'm a YCA fellow at Yale University, and I'm going to talk about the RomulusC simulation, the highest resolution cosmological simulation of a galaxy cluster ever run to redshift 0. But before I start, I want to quickly highlight some of my collaborators. Tom Quinn, in particular, has been a big part of running these simulations, as well as graduate students Angelo Ricarte, who's in the audience, Urmila Chaudhary at Yale/CFA, and Anna Wright at Rutgers, all of whom will have contributed some things to this talk, but I'll only be scratching the surface of all the stuff that they have done and will be doing with these simulations. So before I start, I just want to quickly sort of tell you why you should care about clusters. For one, they represent a really unique environment to study galaxy evolution, right? If we care about how galaxies form, we shouldn't just care about galaxies forming in isolation. We should care about galaxies forming in all sorts of environments, right? We've seen clusters that galaxies forming in these particular environments seem to be very quenched. They experience a lot of extreme things like ram pressure stripping in their, as they interact with the ICM. And then at the centers of clusters, you have these massive galaxies that are experiencing some of the most powerful episodes of AGN feedback, where this sort of mechanism is crucial to regulating star formation. Of course, if we want to actually understand these galaxies fully, you really need cosmological simulations. You need to be able to simulate the growth of all of these galaxies, as well as the growth of the cluster over time, to self-consistently model how each of these cluster member galaxies are evolving over time. Of course, that's not really easy to do and is very expensive and often requires you to go to lower resolution where you aren't even able to resolve the very galaxies you're trying to learn about. This is where Romulus comes in. So the Romulus simulation has 10 to the 5 solar mass resolution and down a 50 parsec hydrodynamic resolution of a galaxy cluster. This allows us to, for the first time, fully resolve dwarf galaxy scales in galaxy cluster environments. This is sort of a whole new way of studying galaxies with cosmological simulations. And just to highlight this, if we look at the resolution of RomulusC compared to all the other cosmological simulations that include galaxy clusters, we are a factor of several to orders of magnitude better in terms of both spatial and mass resolution of anything that's out there today. Now granted, these bigger simulations are all about numbers, right? You have many galaxy clusters. You're not necessarily looking to study galaxies in detail, and that's fine. We are, and so we have one, but we have a lot of detail. I should note that one exception is illustrious TNG 50, which will have very similar resolution and also one galaxy cluster, a very similar size of RomulusC, which I should say is about 10 to the 14 solar masses at redshift 0. So a couple of people have already mentioned the Romulus simulations. These are large-scale, high-resolution cosmological simulations, of which they come in two flavors, RomulusC, which I'll be focusing on today, as well as Romulus 25, a 25 megaparsec uniform volume simulation. But the thing that these simulations do really well is black holes. We do black holes as good as you can do at this sort of resolution, right? And the tagline here is certified organic, free range, locally grown supermassive black holes. The idea being is that we do black holes as good as we can without adding a whole bunch of assumptions. We don't decide exactly where they form or what halos should or shouldn't have black holes. We don't decide where they exist in galaxies or how they move within galaxies. All of that's done self-consistently. And I think critically important, we have very powerful AGN feedback without assuming any sort of characteristic scale as to when that feedback turns on and off. Right? Everything is done such that the properties of the black holes and the galaxies are truly emergent. So we can begin to look at all of these galaxies in this cluster environments and learn what is the difference between galaxy evolution in high-density environments versus the field. And as you can see, there's lots of interesting interactions that are happening, mostly ram pressure stripping as these galaxies are moving through the ICM, that the environment is having a really big effect on their evolution. But before I talk about the rest of the cluster galaxies, I want to quickly focus on the central galaxy, the BCG, which is a massive galaxy at the center of the cluster, which is quenched at redshift 0. It has a final stellar mass that is a bit high, but reminiscent of within a factor of 2 of the average observed galaxy BCG. This isn't the first time people have been able to make a galaxy BCG or a cluster BCG that is realistic in terms of its stellar mass. But what we do get right is the star formation history of this BCG. So this is the specific star formation rate over time of the BCG in blue. And in the data points, we have observations from Bonaventura and McDonald et al. We can see that we match very well with the average star formation history of BCGs across cosmic time. Of course, eventually the BCG does cease forming stars, and this is coincident with a particularly powerful episode of AGN feedback shown in red here, the rate at which AGN is injecting energy into the simulation. And this feedback ends up producing large-scale bipolar outflows, jet-like outflows that reach out to 100 kiloparsecs from the center of the cluster. And I should note that the way we do feedback in this simulation is as simple as you could possibly get. We simply put a fraction of the mass energy of accreted mass into gas particles at 100 parsec scales. Everything else, all of this large-scale outflows, is purely a prediction of the simulation. And while the feedback initially is purely thermal, the actual feedback is obviously very kinetic. But you can also see these large-scale outflows coexist with a cooler, rotationally supported core of gas in the center of the cluster. If we look at it in terms of pressure, we can see ripples going through as shocks propagating outward from this outflow is able to gently regulate star formation in the sort of immediate vicinity of the black hole in the center of the cluster, while it goes outward and regulates star formation on larger scales or cooling on larger scales. And if we look at it in terms of density, we can see, again, this disk of gas that's feeding the black hole is very perturbed as these shocks are propagating through it. And we even produce these nice lobed features in density, which could be observed as radiolobes or X-ray cavities in the centers of clusters. Now, again, I said that we don't choose any specific scale or time when the black hole feedback becomes important in these simulations, which is why these outflows are ubiquitous throughout the entire simulation. But you can see they evolve naturally with time as the angular momentum of the gas, as the outflows sort of interact with the cluster ICM environment. It is only at this time, however, when the feedback becomes particularly strong, sort of continuously for about 2 billion years, does the star formation in the central galaxy finally cease. And we can ask, how does feedback actually regulate star formation in this massive galaxy? And to do that, we can look at the entropy and cooling time profiles and how they evolve over time for the cluster. So you see, blue is low entropy, low cooling time, red is high entropy, long cooling times. And these black lines represent when the cluster is actively quenching. And so you can see nothing is really changing. The feedback from the black hole is not disrupting the structure of the ICM. Right? It's not blowing up gas, it's not superheating it, it's doing it gently without changing the overall structure of things. As a comparison to this, the cluster actually starts to undergo a merger at around redshift 0.2, which is ongoing at redshift 0. This merger with a smaller group does destroy the cool core. It does have a drastic effect on the entropy profile, but not the black hole feedback. So what's actually happening here? Well, this relates a little bit to what Ben was talking about before. It's this idea of precipitation. When you have a hot halo, turbulence in that halo can drive gas to lower entropies than its environment. When that happens, that lower entropy gas will fall to lower radii until it reaches a scale where the average entropy is similar to its own. Okay, so you'll have gas up here on average at high entropy, but some of it will come down here and then will fall towards the center. This sort of raining down into the center of the cluster is becoming more and more an idea accepted by both theorists and observations. Grant Tremmel just submitted a really great paper on the archive, like I think last week or earlier this week, where you can actually see this in action in the center of a galaxy cluster, this gas that's cooling out of the hot halo. But as you can see, the AGN feedback, these particles heated by the AGN, are traveling out to these large distances, and as time goes on, they're sort of carving out this area here from about 10 to 100 kiloparsecs where precipitation is sort of shut down. So you regulate this precipitation of gas on large scales. You don't shut it off completely, but you regulate it. And then as the entropy profile steepens inside, because you're ejecting preferentially high entropy gas as well, this entropy profile steepens and also helps you prevent further precipitation on smaller scales. And so this regulation on both small and large scales from the AGN, controlling this precipitation of gas from the hot halo, is what does your quenching, not explosive feedback, not superheating the gas in the cluster environment. So the BCG, really interesting. You have extremely powerful feedback, which is, again, an emergent phenomenon in our simulations. You have the prediction that says that this feedback should not really affect the structure of the ICM, and it's regulating precipitation, and that's how it does the quenching. So now that I'm done with the more massive galaxy, I'm going to talk about the other galaxies in the cluster, all of these other cluster member galaxies. So the first thing to look at, of course, is how many of these galaxies are quenched. And not surprisingly, most galaxies in the cluster are quenched. So this is the quench fraction of galaxies as a function of stellar mass for RomulusC in orange, and for Romulus 25, the isolated galaxies in the field in blue. And you can see that across all masses, and in particular at low masses, the galaxies in the cluster are preferentially quenched. Now, the interesting prediction here is that observations of dwarf galaxies in clusters are pretty few and far between. There is evidence that there is an enhanced quench fraction, but we can really only get large samples at high masses. So what we're predicting here is that the observations that have taken place that predict this sort of declining trend with mass does not continue to lower masses. And in fact, most dwarf galaxies in clusters are quenched. This enhanced fraction of quenched galaxies continues out all the way out to redshift of 2, looking at galaxies within 2 R200 of this cluster. So galaxies in the cluster environment quench from very early on. Now, how does this happen? This is all due to Ram pressure stripping, right? So the galaxy, as it interacts with the ICM, will lose its gas, and because it's in the ICM, this hot environment, it will not have any other cold gas to gain. So once it loses that gas, it'll be dead for good. And we can see that happening at all sorts of different mass scales, all the way from 10 to the 8 up to 10 to the 10 solar masses in stars. These galaxies come into the cluster, and as they reach the center to high Ram pressure, shown in orange here, their star formation and supermassive black hole activity shuts down very quickly as they experience this Ram pressure stripping. So to highlight this further, I'll choose a little example here. This is a galaxy at high redshift. You can see it goes through some mergers, which cause it to quench for a time, but eventually rejuvenates. As it falls into the cluster, it's a star-forming galaxy. If we look at it right here, as it's sort of making its way to the center, we notice a couple things. For one, you can see the Ram pressure acting on the disk of the galaxy, but it's important to note that Ram pressure doesn't just strip away gas, it also compresses gas in the galaxy. And so this galaxy, star formation rate is actually increasing as it's going toward the center, as Ram pressure is compressing the gas. As it goes further in, we see the gas continues to compress in the galaxy, causing it to be even smaller, more condensed. Now star formation is very high, but now the black hole activity is also ramping up. Because you're pushing gas toward the center, you're driving black hole accretion. And if we look at it here, and we zoom in a little bit, we can see that the black hole is actually doing some damage to the galaxy itself. This black hole feedback is driving these outflows at a few hundred kilometers per second in the center of this galaxy as it's being Ram pressure stripped by the cluster. But all of this happens very quickly, and within a few 100 million years, the galaxy's lost all of its gas and is now this quenched, nothing's really going on in it anymore. No black hole activity, no star formation. And so the corollary to this is if we look at the black holes in the cluster, like the star formation, galaxies in the cluster are much less likely to have black hole activity than in the field. If you look at the Eddington ratio distribution, here I'm plotting the 25th, 50th, and 75th percentile Eddington ratio for black holes in galaxies of different mass. At all masses, the cluster is much more likely to host galaxies that have black holes that are just totally dead, compared to the field where you have some low-level black hole activity, but usually not totally dead. So this is a unique population of black holes as well. Now, the real thing, well, not real thing, but one of the main things that I want to talk about that's very preliminary is the population of ultra-diffuse galaxies in different environments. So this is something we can uniquely do with these simulations because for the first time, we can actually resolve dwarf galaxies in a variety of environments, including galaxy cluster scales. So we have here a little rogues gallery of UDGs that Anna Wright at Rutgers has sort of picked out of these simulations based on their central surface brightness and effective radii. You can see one thing right away, that the UDGs in the cluster environment tend to be more diffuse, and they're not star forming, as I've already mentioned. While in the field, a lot of them are quite blue and more or less smaller radii. And so again, for the first time, we can make a prediction, right? Other than these sets of zooms, we can make a prediction of the fraction of galaxies that are ultra diffuse as a function of stellar mass. And in the isolated case, or galaxies that are not satellites, that are isolated from anything else, these dwarfs are UDGs in the field at about 20 to 40% at around stellar masses of 10 to the 8. As you go to satellite galaxies in Romulus 25, so galaxies that are in groups or so, low mass groups, you get an increase in this fraction. And as you go all the way up to RomulusC, you get that a lot of galaxies are ultra-diffuse galaxies, around 80% at this mass range in galaxy clusters. If we look at their characteristics, right, the effective radii as a function of their G-band magnitude and their central surface brightness, we see, for one, we match nicely with the results from Van Dockum et al. And Yagi et al. 2016, but we can see some differences in the two populations. As I said, in the cluster environment, these UDGs are more likely to be more diffuse, more puffed up, larger effective radii than their field component, their field contemporaries. So the other thing you can notice is that the central surface brightness is also different. In the cluster, we have a lot of these very low central surface brightness galaxies compared to the field. And so this is also predicting that there's a lot of galaxies in the cluster environment that we're still not seeing because observations don't go that low in central surface brightness. So with that, I'll leave you with my conclusion slide. So we have this galaxy cluster simulation. It has the best black hole feedback we can, has the highest resolution anyone's ever done of a galaxy cluster of any halo of this size. We can see that the BCG quenches due to AGN feedback, and we have this interesting population of quenched low-mass galaxies, the majority of which are ultra-diffuse. Thank you for your time. I'll take your questions.
Thank you, Michael. Questions from Michael. Here we are.
Excellent stuff. Really looks amazing. I think if I understood the quenching of your satellites correctly, there's a stripping, ram pressure stripping, and then AGN give you some kick as well. So from the observer side of things, what fraction of the jellyfish galaxies have active AGN in them?
That's a really good question. So that's something that Angelo Ricarte is looking at as we speak in these simulations, so that was a lot of his work here on making these plots, tracking the galaxies back in time and finding when they become AGN. So that's something we're working on for sure. The difficult part, I think, in terms of observations is you notice this phase does not last very long. And so it's this ram pressure activated AGN is really at the very end where the galaxy is just sort of quenching. And that I think tends to be relatively ubiquitous throughout the galaxies are being ram pressure stripped. So we're looking into it, but I'm not sure what sort of observational signatures there'll be.
Phenomenal simulations. You mentioned that it looks like your quenching is through this Voigt precipitation type shutoff. So if I recall, there's like a critical value in the ratio of your cooling time to your free fall time of like 10. Mm-hmm. Do you see that as the
in fact,
threshold?
Yeah. So we do see that when the galaxy is star forming, it dips below that critical value of 10, and then as the galaxy quenches, we can fit into that nice 10 to 30 range, which is exactly what Mark Voigt sees. But that's still preliminary stuff that we're still working through the details on. I could show the plot, but it went away.
We are out of time, so let's thank Michael once again.